Right, this video is going to have a look at the life cycle of stars for Module 2 of GCSE. If you're struggling to find past paper questions for this topic, I suggest you look at the old Module 3 of AQA's old GCSE syllabus, because this is a topic that they've moved from Module 3 to Module 2. Now, what is a star? Well, you've probably heard it described as a giant ball of burning gas. Well, that's not actually true, for a few reasons. What happens, or what happened at the very start of the universe, we think, is that we had a whole bunch of hydrogen. And that hydrogen ended up being clustered together because of gravity. Gravity is a force that attracts things together. So it's really important that you know that gravity is one of the key forces here in attracting things together. And what we ended up with was a ball of fairly hot hydrogen that we're going to call a protostar. Proto just means before. So this is before a star actually gets going. What have we got? Well, we've got a ball of very, very hot hydrogen. The reason that it's hot is because it's being pushed together under gravity. Gravity sucking it together actually increases its temperature. So we end up with a protostar that gets really, really hot. Now, the thing that triggers this into becoming a star is that it's hot enough for fusion to occur. And if you watch another video on nuclear physics in this playlist, you'll see a little bit about what fusion is. But fusion, when two small atoms, such as two atoms of hydrogen, combine to create something heavier, such as helium, and release a huge amount of energy. And the great thing about fusion is that once you're hot enough to start fusion, it releases enough energy to keep that reaction going. And so what you have there is what we call a main sequence star. So this is the major part of a star's life. It's gone through this formative stage and it's actually been birthed by fusion starting, and I've got a main sequence star. It has two things going on inside it. It's got gravity pulling things together, and it has radiation inside pushing out all of the energy from these fusion reactions that are happening are pushing out and being balanced by this gravitational force, which means that this is nice and stable. So I have a stable main sequence star with gravity pulling in, equaling the radiation pushing out from all of the fusion. Now, as we start to run out of hydrogen, the star has to find other things to burn. Now, when I say burn, this isn't burning in the sense of fire. This isn't a reaction where it's burning with oxygen, because there is no oxygen. But what's happening is that fusion is releasing heat energy, and often we'll talk about it burning. But as it runs out of hydrogen, it will swell up. It will become larger and cooler. Now, the core actually still remains very, very hot, and there it will be hot enough to start fusing helium into some higher mass elements. And there are two ways that this can go. If it's a relatively small star, it will become a red giant. If it is an absolutely massive star, and we're looking at multiple times the mass of our sun, this will become a red supergiant. And so these are both very, very similar stages. It's just that they're on different scales. And what's happening here is the gravity and radiation pressures have to find another balance at a different size, but we've still got fusion going on in the core, but now starting to fuse helium into some bigger elements. Now, eventually, we will run out of fuel again. And when they run out of fuel, something has to change. So as we start to run out of, say, helium, which is the next burning, these things will start to change again. Now, a red giant goes for the slightly less exciting route, and it will collapse into a white dwarf. The reason it's white is because there's no Eon dwarf. The reason that it's white is that it will be glowing really, really brightly as it does its final bits of fusion, and that will eventually dull as it cools into a black dwarf. It will gradually lose all of its energy. So there I've got the life cycle of a relatively small star. Now, What happens to a red supergiant is that it will collapse similarly to our red giant, but because there's so much stuff in it, as it collapses, it will actually then cause a sudden and massive explosion, and we call that a supernova. It is the hottest thing in the universe. This supernova, when this star dies so very, very dramatically. Now, what you end up with at the end of that is one of two things. You can either end up with a neutron star, which is ridiculously dense, where the core of the supernova, the bit that wasn't scattered out, the core becomes a very, very dense star made just of neutrons. If it's even more dense, it can cause a black hole, where that neutron star is so dense that nothing can escape, not even light, and things are sucked in to this black hole to become part of this huge, huge amount of mass squashed into a very, very small space. That's the life cycles of stars. Two different routes depending on their mass. Important things to look at. Fusion. This is the fueling reaction. It takes lighter elements and turns them into heavier elements. So all the way through this process, fusion is causing heavier elements to be formed. We go from hydrogen to helium in a main sequence star. And we have all of the elements that you experience in the universe are made in one of these processes. Now, there's a limit to how heavy red giants, red supergiants can make the elements. There's a limit to how far along the periodic table they can go. So you're not going to get anything above iron here. Anything